Hello, my name is Jake, and I'm just going to walk you through what I did for my project. I wasn't very interested in doing the projectile project. I wanted to do something around ciphers and code breaking because that's a great opportunity to practice finding patterns in randomness. As an math major, that's super interesting for me, and the power of MATLAB is super exciting. So I'm going to jump right in. I have a message here that's in code called easy.text. And to start my program, we start at ciphertools.hub, which doesn't do much except reference these other functions. Okay, so we're going to jump right in and run that. Name of the text file, that's the first thing it asks you for, is to load a file. And what it does immediately is cleans it and removes any spurious symbols or spaces and puts it in a nice easy format for processing. Now, a proper code breaker would not do this. They would try to take advantage of every bit of information they can, but for our purposes it makes it a lot easier if we simplify the message. And when the variables come up, you will see that. Okay, so one of the most important things this program's done, first of all, is number 2, display the frequency statistics of English. And the reason that's important is because if you know this data and you compare it to the data of your code, you can learn a lot about the code you're trying to crack. This is the frequency of English language monograms. That just means the single letters. Okay, E is the most frequent. This order will vary somewhat depending on your population sample, what kind of data you're pulling in. But this is about average for most of them. This is the bigram data, and what that means is the relative frequency of pairs of letters. And we like this information because it tells us a lot about the structure of our language. This tells us about the frequency of certain characters, and this tells us how they relate together. And this is a nice format, but really what's useful to us is this curve right here. And this is exactly the same information as this, just lined up and put into order. Okay, you can see it's this very nice curve right here. And when we go to display the data from easy.text, which is option 4, display monogram and bigram data, we immediately see, so this is the frequency data, there's the bigram data, and there's the other set of bigram data. And as we pop this back up, well, first of all, we can see, maybe kind of intuitively, we can say that there's some similarities here. Nothing we could really call out mathematically, except for the fact that there's some common tall spots. Okay, so this is in code, and this is in normal English, and what we're trying to do is figure out what the substitution has been. Okay, so figure 2. Okay, again, this is looking very good. It's looking very much like this code has a structure very similar to English. This curve is almost exactly the same, and this, as I mentioned, these bigram curves can tell us a lot. And we come here, and we can see that, again, we have the same sort of similarity. Not exactly the same, but the same sort of distribution. You might even be able to get pretty far into breaking this code just from this information here. You can see that E is the most frequent letter that appears, and R is the most frequent letter that appears in our code. So you could maybe make some guesses and substitute E for R, and you might be on your way to solving the code, because if you have an E's solved for and you find a 3-letter word that ends in E, well, then you have the word the, and it just gets easier from there. And the reason this is so easy is because this code, easy.text, it's in a simple substitution cipher. So what that means is one letter has been substituted for another. And so that's why structurally, although the letters are different, it's very similar to the English language. Okay, you can see these curves are similar. Now, I won't go into much of a digression of trying to break that code. Like I said, you could probably do it with not too much computing power. We're going to see what happens when we have a slightly more complicated code and why these extra tools are useful. So we're going to exit out of this. Yeah, we're just going to exit out because then we can see all this data that's just been loaded up, which is actually very useful to us. Now it's all in our workspace, so if we wanted to analyze further, it's all ready to go in a bunch of different formats. We've got our basic character frequency, we've got the English monogram. Yeah, but okay, so now we're going to start the program again. This time we're going to load a code that's a little bit more complicated. So we're going to go code.text. Okay, and so we're going to display the monogram and bigram frequency data. And immediately we see that it looks dramatically different from what we had before. And I'm just going to pull up the English data just so we can see again. Okay. And okay. So just switch places there. It seems pretty clear now. It's a little out of order. Here, I'll make this a little easier to see. Okay, it seems a little more clear now. This code is structurally different for some reason, even though we know the text is in the English language. A big assumption to make for a code breaker, but I happen to know this is so, just to limit some of the possibilities. And we can see that, you know, not only can we not tell what the most frequent letter is in this code, we can't even tell what the most infrequent letters are. Like normally, you know, Q's and Z's and X's are a dead giveaway, but somehow there's more noise. You can see that, right? There's a lot more noise. It's been averaged out, and really that's the code breaking and code making game. The code maker is trying to put as much noise into the message to make it harder for somebody who's not in the know to find the distinctive parts of the message and break the code. And of course the code breaker is trying to find that distinctive parts in the noise. And if I draw your attention over here, you can see that this bigram data looks much different. But because we have some history of code making under our human history belt, we know that this shape for bigram data is actually fairly distinctive of particular kinds of code. So this is why this information helps us, is because it's very hard to break a code if you don't know what the method was used to encode it. This is why the Enigma cipher in World War II was so difficult to break, is it had a very specific algorithm based on the day and kind of keys that they used, and so it's very hard to work back from the raw data and find out how it was made. But there are some things we can do to look at this information and try to break it down a little more. So what we're going to do is we're going to hit option number 3, analyze coded message for potential key lengths. Okay, and what this does is you give it a minimum key length to look for, and I'm going to give it 2 because if I were to give it 1, then that'd just be like a simple substitution like easy.text, and we know that's not the case. So 2, and we're going to say 7, and we're going to let it work. And what it's doing is it's breaking the code up. First of all, it assumes a key length of 2 because that's the minimum. And it takes the first letter and it puts it in a pile, and then the second letter and puts it in a second pile, and the third letter goes into the first pile, and the fourth letter goes into the second pile, and basically it splits it up like that. Because how a key works in a code is the key is put end to end, like you repeat the key over and over for as many characters there are in the text, and you line it all up with the text, and depending on what letter of the text runs into what letter of the key, there's an algorithm that takes place. So basically what happens is that you have several substitution ciphers working at once, and the key is literally the key, as in, you know, the correlation between each substitution cipher, if you understand my meaning. And what this is doing is for each key length that I specified in the range is it's breaking it down to the subfrequencies, or the subkeys, and then taking the frequency. That's what this FI, frequency index, and it's referencing this code here. And you can see it's counting columns 1 through 26, letter A to Z, and counting all these letters. And you can see maybe, or you can get some intuition that using the key like this would add some more noise into the code because you're using a different key for different parts of the code. Certain parts of it, if you just a straight frequency count, is not going to reveal the same things it would otherwise. Okay, and so this is kind of the most lengthy part of this. So we're just going to let it work a little bit, and I'll just draw your attention over here. It's building these tables right now. These were here before, but that was from a last run. It's building these tables fresh. And what key length 2 will have in this spreadsheet, it will have the subkeys. Okay, so the code split into 2 sequentially. So 1 to first pile, 2nd to the 2nd pile, etc. And then the frequency counts. Key length 3 will be split into 3 groups. So 1 to the first pile, 2 to the 2nd pile, 3 to the 3rd pile, etc. And with each subkey written out in each frequency table. So basically, this program gives you a lot of raw data to work with. Like, it does a few code breaking things specifically, but really it's a good base to start from, because there's really, as I got into this, I realized a lot of different directions we can go. But in any case, so what this is average IC score for each key length. And IC is incidence of coincidence, if you can dig it. It's basically a measure of randomness. Okay, and so what it does mathematically is it takes each of these subkeys. So you have 2 subsets here because you've divided into 2 for a key length of 2, 3 here, 4 here, and it basically compares it to if you just had a random message. Okay, so it tries to figure out how likely it would be for this information to be generated completely randomly. Maybe I'm not saying that exactly correctly, but the upshot is what it finds is that there's a certain amount of distinctiveness that comes out when you try a key length 7. That is, when you split this whole code into 7 groups, 1 letter into the first, 2nd letter into the 2nd, etc., so on and so forth, you get something that's less than random. Okay, that's very different from if you just had random letters throughout the whole code. So that we know that 7 is probably a likely key length to try. Okay, so I have a tool where we can actually take that key length and do a deeper analysis. And I'm kind of brushing through the math part of this pretty quickly. You'd have to go look up on your own if some of this is confusing to you. I promise you the math isn't that complicated. Just with a little bit of knowledge of statistics, you should be able to figure it out pretty quickly. Honestly, the hardest part of this program was managing the data and getting it all in the right format in the right place so that it gets processed systematically and reliably. And then the math part is a very small, like 2 or 3 lines of code at the center of each of these subprograms. So we're going to move right along. Search for the key, assuming a vinegere cipher, and it says perform option 3 first to build the data set. And this is the data set that this part of the program will use. And this part right here, assuming a vinegere cipher, the reason I do that, it's another limiting factor, so we know what to look for. Okay, and the reason I chose the vinegere cipher to play with is it is a great example of what happens when you are able to add more noise into a code and what makes it hard. And it's also a code that for a very long time in our history was considered uncrackable. And it was cracked before computers, but it was very difficult because of the amount of processing power it takes. It's nice to be able to automate these things. So we found out that with a key length 7, the data does something interesting and slightly less random than with the other key lengths. So we're going to process this data assuming that we're looking for a key of length 7. Display correlation graphics hour. No, this is just a visualization of some of the correlations. We're going to put that on no for now. Okay, so I did that all pretty quickly. And I'm just going to go out of this program so it updates the data. And I'll show you what these charts mean in just a sec. But first I want to show you what was built there, and it did it pretty quickly. Yes, God bless MATLAB. And I'm going to show you what it built. So this is the correlation data. And you can see here we've got some big matrices separated by some zeros. The zeros are just spacers. And what this is so for the first subset, it compares each letter. So assume 3 to 28, that's your 26 letters, A through Z. Takes the first letter and takes the frequency count and compares it mathematically to every other letter, the expected frequency in the English language. Okay? So it takes the letter A, how many times does A appear in this code, and then compares it. And it's using this chi-squared function, which in statistics is a method for comparing and finding out how related two sets of data are. Okay? And then it does this for B and C, and it goes all the way through, and it basically just crunches those numbers. And the reason we have multiple matrices here is because this is in fact doing this for each letter of the key. Like I said, we had determined that it was a key length of 7, which means a key of 7 letters, creating 7 subsets, because remember, you line the key up back to back, and each letter of the key decides how the algorithm will be applied to that particular letter in the code. Okay, so basically what this data is just a data for a bunch of different substitution codes. And what we try to do with this data is find basically the lowest pattern. And what I mean by that is, so if you run along here and we look for a good example, okay, so 18, check this out. This means that the letter A is very close to the letter, I'm not sure what the 18th letter, whatever the 18th letter is, the alphabet is. Statistically, they're almost exactly similar comparing with these other numbers. Okay, so we know that the letter A statistically appears as about as much as we would expect the 18th letter of the alphabet to appear. Okay, so that's a good indication that that's a great substitution there. Okay, so then we go to the next column, and that might be a likely candidate. That might be another one. But you see, okay, so because there's one letter substituted for another letter, there's no double substitutions or anything like that. What we're looking through is trying to pick a combinations of substitutions that results in the lowest number if you were to add all these numbers up, basically. So if I were to take this one and say, okay, we've substituted A for the 18th letter of the alphabet, and then taken this one and B, well, we've substituted it for B just to be tricky, and C we've substituted for D, etc. and so forth, and to add all those numbers up, basically, I mean, ideally what we would do is take all the possible different ways of adding that up, but that's 26 factorial different calculations to do, and that's probably beyond the lifespan of my computer hardware. Now, because it is a vinegere code and that applies an algorithm a specific way, we know what to expect. And that's a big assumption in code breaking, but I just wanted to show you this because of give you an idea of what's possible once you have this kind of information. Okay, but the computer knows that it's a vinegere code, or it's assumed as such, and it just so happens that that's the case, and I know this because I encoded it. And it has taken each right on, okay. It has taken each subset and it has crunched the numbers and found the combination of substitutions which results in the highest, or I should say, the lowest difference from the frequencies of the English language. It finds the substitution which results in the closest approximation to the frequencies of the English language. And like I say, I'm going through this really quickly. If any of this is interesting and if I'm confusing you, please do look it up. It's not complicated at all. 5 minutes on Wikipedia and you'll understand what I'm talking about. Okay, so what it's done is, so for the first set, like I said, what is the subset that has been encoded with the first letter of the key? It is gone and it has done all the math and has found for us that the letter R is a likely candidate. And what that means is that if you were to have A in the message, it would instead appear as an R. Okay, now how do you apply that to the rest of the message? Well, actually what that means is if you had a B, it would be an S. And if you had a C, it would be a T. And so that's what the vinegere cipher does, is that once you have that first jump, it rotates the rest of the letters likewise. And the reason it makes it more complicated than the easy code that we did is that it changes spots. So now the second letter, because it's the second letter of the key, is a U. So if you had an A, it would be a U, and if you had a B, it would be a V and a C, and then when you got to Z, it would go back round again. So we know the second letter is U, and we continue like this. So we have R, U, S, S, A, or I, A, N, and the code is Russian, or the word Russian. Okay, so now we can just test that and apply the key. So apply the key, assuming a vinegere cipher. Again, like I say, I've made this program very specifically apply the key in this way, in the way I just showed you, that kind of rotating factor. Just to kind of demonstrate the kinds of things we can do. Got to start up the program again, that's okay. But really, once you've got that core, you have that correlation table, that matrix that I showed you, and you can start playing around with all kinds of methods depending on for finding correlation and deciphering it. You can take examples from history in terms of what might be likely. Input cipher key, so we know that it's Russian, and it's just going to apply that. Now, any of you who are up to date on modern encryption practices know that all this is relatively academic, more kind of an interesting thing and some basics to learn. Your current cryptographic technology is basically beyond most computing power to crack, and about as impervious as we can get. But like I say, it's a good opportunity to practice finding patterns in random data. And this is where we're just checking to make sure the program worked properly. It's applying the key. So over the whole message, this is the code right here put into a big long list. And so it's actually applying it in reverse. So whatever letter came first and had an R applied to it to create this letter, supposedly K, it's doing it backwards. So and it's doing that for the whole message for each letter. So it's just working now. I can just take a moment while I'm doing this and just talk about, like, if I were to continue. Oh, there we go. We're done. If we were to continue evolving this program, there's certainly a lot of directions and a lot more improvements that can be made. Right now, it's a little obscure, specified, and not very user-friendly. But like I said, using this correlation data and using this information here, there's a lot of directions we can go, a lot of different kinds of codes we can program MATLAB to look for. And I think probably what I would do if I were to continue improving upon this program, I'm just going to exit here so it uploads the data and we can take a look at the decode attempt. Probably what I would do is add a process for adding cribs. So that's like, a crib is when you know something about your code. So you can basically makes the computer's job a little bit easier if you already know what some of the substitutions are. In World War II, how they cracked this super impossible code, the Enigma code, is they were able to find a crib, in that every message either started or ended with the words Heil Hitler in code, and that kind of constriction on like what they knew allowed them to get a foothold to break the code. So cribs are very important. So I wish I could add a feature for adding those. But just so we look now, look, here is your uncoded message, and look, we have the screen the script of The Big Lebowski, which is exactly what I put into code. Yeah. So, like I say, this program's rather specific. Like you can only directly break a vinegere cipher. But with this data, you could probably do a lot more, and it wouldn't be much of a jump to be able to start breaking other codes. But time and practicality kind of limited me from putting anything else in here. Nonetheless, I think I've kind of demonstrated the concept. Yeah, and I had a lot of fun doing it. So thank you for your time and attention, and I hope you found this entertaining, if not informative and interesting. So thank you for your time.